This is the Algebra 1B semester exam review for Unit 3. On your exam, you will be given a formula sheet. Really for Unit 3, we're going to have to focus in on this one, the definition of the residual, but just remember that this formula sheet is here to help you. Question 1. Ms. Tran looks at the scores on her first Algebra 1 test. They are listed below. She cannot decide how to display these scores, so she makes two different displays. So we're going to have to make a box plot of the data and make a histogram of the data. In order to make a box plot, we have to put the numbers in order from least to greatest. So when we do that, we're going to get a list of 41, 45, 66, 68, 68, 73, 74, 76, 77, 79, 81, 81, 81, 88, 91, 94, and 99. A good technique to make sure that you're correct is to count how many data points you had originally. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then count how many you wrote out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This will help make sure that you didn't miss a number. Next, we need to find our 5 numbers: the lower extreme, the lower quartile, the median, the upper quartile, and the upper extreme. So the first thing I'm going to find is the median. We can find the median by, crossing off the smallest and the highest, smallest and the highest. But I really don't recommend crossing off the numbers because you're going to have to use them for other things. So if you want, you can put a dot at the top. Just to indicate that you're going back and forth, back and forth, back and forth, back and forth. And so what we can see is that our median is going to be 77. We also know that our lower extreme is going to be 41 and our upper extreme is going to be 99. Next, we need to find our lower quartile and our upper quartile. And to find the lower quartile, we're taking the median of the lower half of the data. Upper quartile is going to be the median of the upper half of the data. We never include the median, so if there were an even number of data points and your median was in between two numbers, you would include those two numbers. You just don't include the median. So to find the median of the lower half of the data, I'm going to find the middle number, which is going to be in between 68 and 68. So my lower quartile is going to be the mean of these two numbers. So I'm going to add them together, divide by 2, and I'm going to get my lower quartile is equal to 68. I'm going to do the same thing for my upper quartile. It's going to be in between 81 and 88. So 81 plus 88 divided by 2 is going to be 84.5, and that's my upper quartile. So I'm going to use these 5 numbers to make our box plot. I'm going to put dots where my lower extreme and my upper extreme are, and I'm going to put lines for the lower quartile, the median, and the upper quartile. And those 3 lines are going to make our box, and then our whiskers attached to our lower extreme and upper extreme. I highly recommend that you label your numbers: 41, 68, 77, 84.5, and 99, just so whoever's grading your exam knows exactly what points you are trying to graph. So this is our box plot. Now, if in your class you learned how to find the outliers, I'll just do that really quick. Our outliers are upper quartile plus 1.5 times the IQR, and the lower quartile minus 1.5 times the IQR. My IQR is going to be the upper quartile minus the lower quartile. So 84.5 minus 68, which is going to equal 16.5. So to look to see if I have an upper outlier, I'm going to do the upper quartile plus 1.5 times the IQR. My upper quartile is 84.5, and I'm going to add that to 1.5 times 16.5. This is going to equal 109.25. Since my highest number is 99 and that's less than this 109.25, I do not have any upper outliers. Now I'm going to do my lower quartile minus 1.5 times the IQR. So that's going to be 68 minus 1.5 times 16.5. And that's going to equal 43.25. Well, what I see is 41 is less than 43.25, which means I'm actually going to have an outlier at 41. If I were to change this box plot to incorporate that, I would plot my outlier at 41, and then I would make my new lower extreme my next lowest number, which would be 45, and connect it to my box. Nothing else changes. This is all incorporated after you find your 5 numbers and everything like that. Either answer will be accepted on your exam, so keep that in mind. For question 1 part B, we're supposed to make a histogram of the data. And we need to use intervals, the intervals shown for our display. So basically we need to make a frequency table first. We have 0 to 9, 10 to 19, 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. And what I want to see is how often do my numbers occur in each interval? Well, my lowest number is 41, so I know that I'm going to have a frequency of 0 for all of these. So between 40 and 49, I've got 2 numbers. Between 50 and 59, I have 0 numbers. Between 60 and 69, I have 3 numbers. 70 and 79, I have 5 numbers. 80 and 89, I have 4 numbers. And between 90 and 99, I have 3 numbers. And if we add this all up, it's going to be 17, which is the number of data points we have. So now I'm going to graph these. So I have 0 all the way up until 40 to 49, which I have 2. So I'm going to have essentially a bar graph, even though this is a histogram, that goes up to 2. Between 50 and 59, I have 0. But 60 to 69, I have 3. 70 to 79, I have 5. 80 to 89, I have 4. And 90 to 99, I have 3. And this is my histogram. So finally, for part C, it says use your displays to describe the data. You should use measures of central tendency, variability, and distribution in your description. Well, let's talk about it first, and then I will write out my actual answer. But basically, my box plot tells me that my lowest score is 41. I also know that this was an outlier if you calculated that. It also tells me my first quartile score was 68. Tells me my median was 77, tells me my third quartile score was 84.5, and it tells me that my highest score was 99. A box plot also shows me the range of my data, which is from 41 to 99, which gives me a range of 58. It also tells me my inner quartile range, meaning the range of my middle 50%, the range of my box. That range is from 68 to 84.5, which gives me an inner quartile range of 16.5. Because this whisker is longer than this whisker, I can say that it is probably skewed slightly left. My histogram shows me that my data is skewed left because most of my data is here and I have a little bit of a tail on the left-hand side. I can also see that most of my scores were in between 70 and 79. I can see that most of my scores were greater than 60, and I only had 2 scores in between 40 and 49. I can see that the range of my scores is about 60 because they go up to, approximately 100 to 40. So 100 minus 40 is 60. And looking at the center, I've got 2, 3, that's 5 points on this side. I've got 3, 4, 5 points here, 2 and 2. Somewhere in here is my center, my median. So my median is going to be somewhere in the 70s. So that really describes my data. I used measures of central tendency, really median and mode, variability, and distribution in my description. And now I'm going to have my answer appear in written form. So here's my answer written out. The box plot tells me that the lowest score was 41, which was an outlier. The first quartile score was 68. The median score was 77. The third quartile score was 84.5, and the highest score was 99. The range was 58, and the interquartile range was 16.5. The data is probably skewed left. The histogram tells me that the distribution is skewed left, and that the most scores occurred between 70 and 79. Most of the scores were greater than 60, with only 2 scores in the 40s. The range of scores is about 60, 100 to minus 44, and the center appears to be in the 70s. Question number 2. The following box plots show the distributions of test scores for 2 math classes. So we have Math Class 1 and Math Class 2. From the list below, circle which ones you cannot determine from the box plots. Well, we can determine the median because we can see that right here. But we cannot determine the mean because we don't know any of the data points for certain except for the lower and upper extreme. We can determine the range because it's the upper extreme. For instance, here's 100 minus the lower extreme, which is 50. We can determine the interquartile range because that's the range of the box. Upper quartile minus lower quartile. However, we do not know the individual scores for each math class. We do know the quartiles, which is the upper quartile and lower quartile. We do know the distribution skewness by kind of looking at the whiskers. We can see this looks like a normal distribution, whereas this might be skewed to the right a bit. And we do not know the number of test scores because, as I said, we don't know what the individual scores are. Part B says, based on what you know about box plots, which class performed better on the test? Give at least 2 reasons for your answer. Well, I would say for sure that Math Class 2 performed better. And there's many reasons. For instance, all of the data is 70 or above, whereas only half of the data in Math Class 1 is 70 or above. So basically, all of Math Class 2 performed better than 50% of Math Class 1. We can also look at the medians, which is a measure of central tendency, meaning average. And Math Class 1's average is a 70 versus Math Class 2's average, which is an 80. We can see that, 50% by looking at the median, 50% of Math Class 2 scored better than, therefore, 75% of Math Class 1, among other reasons. So I'm going to type in an answer so you can see written out what this answer would be. So, based on what you know about box plots, which class performed better on the test? Give at least 2 reasons for your answer. Math Class 2 performed better on the test. This is because they had the higher median or average, of 80 compared to Math Class 1's median of 70. 50% of Math Class 2's scores were above 80, while only 25% of Math Class 1's were above 80. All of Math Class 2's scores were above 70, while only half of Math Class 1's scores were above 70. Part C asks, which data set has greater variability? Justify your answer. Well, the more spread out the data is, the larger the variability. So we can clearly see from the box plot that Math Class 1 has greater variability, but we should prove that. And the way to look at variability is to look at the range and the IQR. So Math Class 1, the range is the upper extreme minus the lower extreme. The upper extreme is 100, the lower extreme is 50, so Math Class 1 has a range of 50. The IQR is the upper quartile minus the lower quartile, so that's about 80 minus 60, which is going to equal 20. Math Class 2, on the other hand, the range, again, is the upper extreme minus the lower extreme, so that's going to be 90 minus 70, which is going to be 20. And the IQR is going to be the upper quartile minus the lower quartile, which is 85 minus 75, which equals 10. So Math Class 2 has a smaller range and smaller interquartile range than Math Class 1, which means Math Class 1 has greater variability. And to put that in writing, we have this. So, which data has greater variability? Justify your answer. Math Class 1 has greater variability. This is because the box plot is more spread out for Class 1 compared to Class 2. The range is larger for Class 1 as well as the IQR. The larger the range and the IQR, the more varied the data is. Question 3. Look at a scatter plot and the line of best fit below. A residual for a value of x is the difference between the observed actual value of y and the predicted line of fit value of y. So they're asking us to find the residual when x equals 3, 6, and 9. So if we remember, and it says it right here, it's going to be observed minus the predicted. So when x is 3, here's our observed, here's our predicted. So our observed is going to be 70 minus our predicted of 20, and 70 minus 20 is 50. When the residual, what is the residual when x equals 6? Well, here's our observed, here's our predicted, so we have 60 minus 40, which equals 20. Finally, when x equals 9, here's our observed, here's our predicted, so 70 minus 60 gives us a residual of 10. Question 4. In the 1980s, it was found that the correlation coefficient between the amount of ice cream sold and the number of crimes in New York City was R equals positive 0.97. Does this mean that an increase in ice cream sales causes an increase in the number of crimes? Explain your reasoning. So no, it does not. R equals 0.97 does show a strong correlation, because remember, the closer to 1 you get, the stronger the correlation, but it does not show causation because they are unrelated to each other. The amount of ice cream sold does not cause crime to increase. How much ice cream is sold and how much crime there is have nothing to do with one another. For part B, it says, give another example of two variables that might have a high correlation coefficient, but the change in one of the variables does not cause a change in the other. There are many examples that you can come up with. So I'm just going to come up with one, which is the following. So the number of sunglass sales and the number of ice cream sales could be an example. So we know that the cause of temperature or summer months could be a reason or the cause of an increase in sunglass sales and ice cream sales, but neither of these are actually the cause of the other, meaning ice cream sales does not cause an increase in sunglass sales and vice versa. There are many other examples that could work for this as well. This is just one, but it's an example of two variables that might have a high correlation coefficient, but the change in one of the variables does not cause a change in the other. Question 5. Sammy is interested in the number of visitors that will come to the beach as a function of the temperature. Below is the data and a scatter plot that Sammy has collected. So we have our data and we have it plotted on this scatter plot. Part A says, what is the relationship between the temperature and the number of visitors to the beach? Well, we can see that as temperature increases, and we always look at x increasing, what's happening to the y's. But as the temperature increases, my y's, my visitors, are also increasing. So we can see that there is a positive correlation. It also looks like a fairly straight line. I mean, it's not perfect, obviously, but I would say we could figure out that is a strong correlation as well. So as the temperature increases, the number of visitors to the beach also increases. There is a strong positive correlation. All right, part B says circle the value that best describes the value of R, the linear correlation coefficient. Justify your answer. Well, as I said, the data looks like it's a fairly straight line, so we know that it's going to have a strong correlation, meaning that it's going to be close to 1. It's not in a perfect straight line, so it can't equal 1. And because it's a positive correlation, our R has to be positive as well. Since our R has to be positive, we can eliminate this one already. Because it's not a perfectly straight line, we can eliminate it equaling 1. And because it's a strong correlation, we can eliminate 0.05 because that means that there's no relationship. So we're going to pick R equals 0.89. We do need to justify our answer. And we can do that with an explanation of why we picked 0.89. The data lie pretty close to being on a line, so it has to be close to 1. It does not form a straight line, so it is not 1. Additionally, it is a positive correlation, so R must be a positive number, hence R equals 0.89. Continuing question 5, we have the results of finding the line of best fit on a calculator. From the information above, write the equation of the line of best fit. So I'm going to deal with letting V equal the number of visitors. And I'm going to let T equal temperature in degrees Fahrenheit, just so I can easily relate it to the context of my problem. So my equation of line of best fit is going to be V equals 32T plus 256. Because we have Y equals AX plus B, but A is 32, so 32X plus 256. So V equals 32T plus 256 is just the equation written in terms of the context of the problem. Next, D. What is the slope of the line of best fit? What is the meaning in the context of this situation? So my slope is 32. Slope is written as change of y over change of x. So if I'm going to write 32 as a fraction, I'm going to have 32 over 1. Well, what are my y's? My y's are visitors, and my x's, my 1, is degrees Fahrenheit. So my slope is 32. This means that for every 1 degree Fahrenheit increase in temperature, the number of visitors to the beach increases by 32. Next, what is the y-intercept of the line of best fit? What is its meaning in the context of this situation? Well, the y-intercept is 0, 256. This means that when it's 0 degrees Fahrenheit, we have 256 visitors. And that's what the context is. So the y-intercept is 256. This means that when the temperature is 0 degrees Fahrenheit, there are 256 visitors at the beach. Part F says, what does your line of best fit predict for a temperature of 88 degrees? Well, our line of best fit is V equals 32T plus 256. So I want to know what is V when the temperature is 88 degrees. So I'm going to substitute in 88 for my temperature. And 32 times 88 is 2,816. And I'm going to add 256 to that. And I'm going to get 3,072 visitors. So there will be 3,072 visitors predicted when the temperature is 88 degrees. What is the residual at a temperature of 88 degrees? So remember, residual is the observed minus the predicted. Now we have to go back to our table of values, which is on the previous page, to see what our observed value is at 88 degrees. So look in the table and see when t, or when x is 88, we get a y value, number of visitors, of 3,151. Our predicted value is what we just found in part F, which is 3,072. So when we subtract 3,151 minus 3,072, we get 79, which is our residual. Finally, part H, according to the line of best fit, at what temperature will there be no visitors at the beach? Explain how you determined your answer. Well, we can determine our answer by showing work. So we're going to use the equation V equals 32T plus 256. And we want to know what is T when V, number of visitors, is 0. So the first thing I'm going to do to solve this equation is subtract 256 on both sides. 0 minus 256 is negative 256, which equals 32T. So if I have negative 256 equals 32T, to get T by itself, I'm going to divide both sides by 32. And I'm going to get T equals negative 8 degrees Fahrenheit. So there will be no visitors when the temperature at the beach is negative 8 degrees Fahrenheit. Question number 6. A carnival game kept track of the ages and what type of prize, if any, that people won at the game. The results are shown in the table below. Part A says, of the children who played, so these are the children who played. There were 50 of them. What fraction won a big prize? And that would be 8. So 8 out of 50 children was the fraction that won a big prize. We can simplify this down to its simplified fraction, which would be 4 over 25. So what fraction won a big prize? 4 out of 25, or 8 out of 50. What fraction of the small prize winners, so that's this row right here, so there were 100 small prize winners, what fraction of them were adults? And that would be 82. So 82 out of 100 small prize winners were adults, or if we simplify that, 41 out of 50. Part C says, what fraction of the total number of players, so that's our total of 200, how many of them were children? So we can see 50 out of 200 were children, and that simplifies to, that simplifies to 1/4. So 50 out of the total number of players, out of the 200 total players were children, or 1/4 of the total amount of players were children. Finally, Part D says the percent of children who won a small prize was less than, equal to, or greater than the percent of adults who won no prize. So the first thing we need to figure out is the percent of children who won a small prize. And the percent of children who won a small prize, here's our small prizes, is 18. So right now I'm just going to write that as a fraction, 18 out of 100. Our percent of adults who won no prize, so here's our row of no prizes, 56 out of 80 of them were adults, so that's going to be 56 out of 80. Now to make these into percents, we're going to take, for instance, 18 out of 100, divide 18 by 100, and then multiply by 100, and we're going to get 18%. 56 out of 80, we're going to divide that, multiply by 100, and we're going to get 70%. So the percent of children who won a small prize is less than the percent of adults who won no prize. Question number 7 says Montgomery County middle and high school students were asked if schools should start later in the day. Here's some information about their responses. So the first thing we have to do is complete the table. I'm going to start with my totals over here because I know I have 350 total and 250 of them are high schoolers. So if I do 350 minus 250, I'm going to get the remaining amount, which is 100. So there were 100 middle schoolers, 250 high schoolers for a total of 350. Next, I'm going to work with the row of middle schoolers. Out of 100 middle schoolers, 30 said yes. So 100 minus 30 said no, which is 70. Next, I can work with this row, the number of high schoolers. There were 250 high schoolers total. 225 of them said no, and when I subtract that, I get 25 that said yes. Finally, we can work with each column, and to get the total, we add them together. So 30 plus 25 is 55, and 70 plus 225 is going to be 295. And just to check our work, 55 plus 295 should add up to 350, which it does. Our next question is, what fraction of high school students said yes? So we're looking at all the high schoolers, which is 250, and how many of them said yes? Well, 25 out of 250 said yes. And if we simplify that, we could also say 1/10 of all high schoolers said yes. Part C says, of the students who said no, so here we're looking at the 295 students that said no, what fraction were middle school students? So here we're looking at 70 out of the total 295, and that can also simplify to 14 out of 59. So out of the students who said no, or out of the 295 students who said no, 70 of them were middle schoolers. Or 59 out of the 59 students who said no, 14 were middle schoolers. Finally, part D says of all the students, so this is us working with our total of 350, what fraction were high school students, all right, high school students who said no. So we're being very specific in seeing out of the 350 students, how many were high schoolers who said no. So that is going to be 225 out of 350, or I can simplify that to 9 over 14. And that is the end of the Algebra Semester Exam Review for Unit 3.